Hello and welcome to lesson 3 in this series of YouTube videos about the neutron detector array at NAND and its analysis using root. All the files that you need for this lesson are located in my website amberchatterjee.com, and if you have any doubts and questions, you are welcome to contact me on my email address. So you can get the files you need from the website by going to nand03.tgz, which is again a tar zip file which contains the files. In addition to that, you will need some files from the previous lesson, and that you can get from nand02.tgz. Let's go on to what the goal is. We are trying to build in this lesson a number of neutron spectra, neutron energy spectra. Neutron energy spectra, which we are going to build, will be having 73 detectors. So its correspondence is that there are going to be 73 detectors, and we are also going to slice the multiplier proportional counter, the forward angle multiplier proportional counter, into 12 slices in the demo program. So there will be a total of 876 neutron spectra which we are going to prepare and which we are going to store. So I am going to write the program in a structured way so that the program will be short. It will be very small number of lines, and yet the program can deal with any number of slices. So you don't have to have 800, you don't have to have 12 slices. If you would like to run with 6 slices or more than 12 slices, or with even just one slice, like how people consider just only one slice, big slice in the middle of the detector. So the program can deal with all these situations. Each slice can have an arbitrary position of the slice. The values of the x limits are x1, x2, and y1 and y2 for each slice. And this also coding will work for any number of detectors. So when you want to have in your experiment, you may be having less number of detectors or more, you can change that easily. So this is how the goal is for this lesson. Now let's go to the files which you need. The files which you need in this, I have them here so you should have a directory, and in that directory you should place the files. You will actually get it in this tar zip, and when you unpack the tar zip, you will have almost all the files here except for this work.root, which you should get from the previous lesson. Okay, so the output of the program is going to be in a single text file, and that text file will be called neutron spectra.txt. Later on you will learn from subsequent lessons how you can analyze these neutron spectra with moving source fit. We will also need the number of fissions corresponding to each slice, so the program will also output that. The gates which we apply, so the gates which we apply are basically cut T1, T2, which is the fission gate created from the two multiwire proportional counters, and this was saved inside work.root in the previous lesson. And then there are neutron selection cuts, and these cuts are one cut for each detector, and these two we had created and we had saved it inside work.root in the previous lesson. Today we will be working on the x1, x2, y1, y2 conditions for slicing by dividing the multi-wire proportional counter, the forward angle multi-wire proportional counter, into a number of slices. For my demo program, I will be using 4 by 3, that is 12 slices. Now in most of the experiments, it is actually MWPC 1 which is in the forward angle. But in our sample data which I am using here, the MWPC2 was the one which was placed in forward angle. So when you use my program to analyze your data, you must take care that you change the parameter numbers according to which MWPC is in the forward angle for your experiment. In every experiment, you need to also calibrate the multi-wire proportional counter. This is usually done by placing a mask in front of the MWPC. Either this can be done just before the experiment starts, or it could be done at the end, and you could do it with beam, or you could also do it with the source. The numbers which you see in my code, that is mx, cx, my and cy, these are the calibration parameters. Mx and my are the slope parameters, cx and cy are the offsets. So the position is calculated by the difference between left and right, or in the case of y, the difference between up and down. The offset can come because of the cable length. That you see, these are actually time difference. So depending on the time for the particular wire, you get the values of the channel number, and to get the channel number converted to a time in nanosecond, and then converting that time again into a position in centimeters, that's what mx does. And if there is a small difference between the left and right, this could happen, for example, due to cable length or some difference in the electronics, then you might have an offset, and that I represent by cx and cy. So in my case, the dimension of the multi-wire proportional counter was 20 centimeters by 10 centimeters, 20 centimeters horizontally and 10 centimeters vertically. For you, this could be different. So these are the changes which you would have to make in the code for your particular data. I'm going to start with program 5 and 6, which are more like demo programs without any real ultimate use. The ultimate program is program 7. Program 5 and 6 will help us to understand the 2D position spectrum for the multi-wire proportional counter, and program 6 will help us to work out how we can make the slices. The actual building of neutron spectra will be done in the final program, that is program 7. And I explained already the other files that you will need. They are given over here. The file list.txt, this is available from lesson 2. This is the chain of files which you are going to analyze. gpos.txt, this is the position of the gamma ray peaks for each of the detectors, and this we constructed in lesson 2. The paralist.txt is of course the most important to open this root files, and the list of parameters is given here. This also we prepared in lesson 2. Slice data.txt we are going to do now. This will I'm going to explain how we prepare this file. For today's demo, we will make 12 slices, and that will be entered in slice data.txt. And work.root, so this was where we saved all the cuts, the fission selection cut as well as the individual neutron selection cuts for all the detectors. So this work.root was already constructed in the previous lesson. Let's start with program 5. So program 5 calculates the position of the detected fragment in the forward angle MWPC inside an event loop. And for the sample data which I have, it is MWPC2, and accordingly the parameter 6, that is the 7th parameter actually, but since indexing starts from 0, P6, so P6 corresponds to the XL. MWPC2, its X position left side, and P7 that corresponds to MWPC2 XR. So these are the equations I will use. These two equations actually I will use them for my getting the positions X and Y. In case it is not MWPC1, it is not MWPC2, but actually MWPC1, which is at forward angle in your data, then you can change in your code the appropriate numbers of these P indexes. And then in the first program, we will learn how to make this two-dimensional position spectrum. This is a 2D histogram of the fission events in MWPC. And then my MWPC has a dimension of 20 centimeters along the x direction, that is going from -10 to +10 centimeters. And in the y direction, it is going from -5 to +5, that is the height of the MWPC is actually 10 centimeters. We usually try to avoid the complete detector, and we just leave out a little bit along the edges, so that in case the signal is not very clean along the edges, then that portion of the detector we avoid. So normally we keep the effective area of the MWPC slightly smaller than the full. I think you could also do it with the full, but anyway, here I have done it taking the full acceptance as -9 to +9 in the x, and -4.5 to +4.5 in the y. If you were to think of 6 slices, I'm going to do actually 12 for this demo, but if you were to make, say, 6 slices, then this is what it would look like. Here you have the slice numbers 1, 2, 3, 4, 5, 6, and these are the x limits and the y limits. And these limits are what you have to put in slice data.txt. When I prepare my slice data.txt, I'm going to make 12 slices like this. The 12 slices will be as numbered here, and these are the x and y limits for these 12 slices, and these are the numbers which you will have to put inside slice data.txt, which we shall see. Alright, so now before we go to program 6, we should see program 5, which will help us to actually get this picture. So this picture will come from program 5. So let's run program 5. Program 5 is located here, and so this is a structured program having very few lines, and the aim of it is only to display for you the two-dimensional position spectrum of the multi-wire proportional counter. And this looks like this. It is similar to before, nothing much new. What is new is that we construct, these are the 3 spectra which we are going to construct. So these are the constructors of the 3 spectra. These are the 2 one-dimensional spectra of the x and y positions, and this is the 2-dimensional spectrum of the multi-wire proportional counter xy position. I've decided to have 512 channels along both x and y, and my spectrum needs to go from -10 to +10, but I've chosen -12 to +12 so that you can see some little bit of empty area, white area around it. Similarly, in the y, it is actually -5 to +5 because my height is 10 centimeters, but I've chosen a little extra, -6 to +6, so that you have a chance to see beyond the detector where nothing should actually come. So that's about the constructors. And then how do we fill them? So we make the loop over the entries, and then we construct the x. I've explained in the slide how you get the x position and the difference between left and right, or the difference between up and down for y direction. And these are the 3 fill commands. And then let's display them. So I have displayed I made 3 canvases, and I have drawn on 3 canvases, staggered a little bit so that you can see the 3 spectra. Mainly we are interested in this 2-dimensional. The first 2 are just just for fun, but what we really need to look at more seriously is this 2-dimensional xy. So let's have a look. Let's compile, and then we run it. The compile always you will find in all my programs the compilation command is available at the top. So what do we need to do? We go here, and then we open a terminal. So I opened the terminal, and so let's inside the terminal now. Let's try to compile it. So this is my compilation command which I have pasted, and we are going to compile. So here goes. This is the compilation. Now the compilation is over. Now we are going to run Now when I run it, you'll get actually an error message which you need to ignore because it's connected with my root installation, which I will correct later on. For just for the present, just forget about this error message. Just concentrate on how the running goes. Okay, so here this is the error message. Don't read this. Come to this. This is my result. These are the three spectra, and this is the one which I want. This two-dimensional XY. So these are the wire spectra. These are the multi-wire proportional counter one-dimensional spectra in the X and Y directions. You see here the wires. These wires which are part of the MWPC, they are shadows. They prevent also the particle from going inside. So that's why you get these spikes. And the other thing is that you also get a reduction of counts near see, look here. So I have done the calibration. The calibration with mask has been done, and I have put in the calibration numbers in the code. And so when the X and Y positions are calibrated, then only you will get these limits -10 to +10, and also along the Y -5 to 5. So now, but near the edges, when you reach towards the end, you'll find that the counts are less, and this is happening not because there's really an effect of the fission angular distribution. That's not the point here. The reason why it comes less is because the detector surface is actually flat. It's not curved. So when you come to the edges, the distance from the target is more. In the center, it is the minimum, and as you go towards the sides, then the solid angle per square centimeter of the detector that comes down. So effectively, the parts of the detector which are far away are far away. The edges of the detector are far away from the target. So that's why you see this drop of counts. But anyway, that's not relevant here because we are going to normalize our data by dividing by the total number of fissions for each slice. So it's not that I should not take slices here in the edges where the counts are less. We can take slices there because we'll be normalizing the slice data, and for normalizing we'll be dividing by the number of fissions. So don't worry about that part. So that was about program 5 and how we displayed this two-dimensional XY position, and we got this picture. Now we are going to see how we can slice it. So we have to prepare another program. We will do that. So let me stop this program, and first thing to do is to prepare the slice data.txt file. So this file has to be prepared by you. Of course, you have it when you unpack. So when you unpack nand03.tgz, you will actually get this file. But for your actual data and for any other data, you have to actually change this according to how many slices you are going to work with. So this file will change depending on your decision as to how many slices you want to work with. My demo is for 12 slices, 4 by 3. So 4 cross 3, 4 divisions along X. These are the X limits which I explained in the slide, and this is Y 3 slices, and these are the slice limits along the Y direction. Now we are ready to run program 6. So I don't need now program 5. I will go to program 6. Program 6 is here, and what's new in it is that it reads the file slice data.txt. So this is the new function from here to here, which wasn't there earlier. What it does is that it tries to read this file slice data.txt, and it finds out the slice limits in both X and Y direction. So that's that, and these are the calibrations X and Y, which was also there in the previous program. But now what's new is the slices. So these are the limits x1, x2, y1, y2 and I have, because it's a structured program, I like to keep here a hash define for how many slices you can have. I've decided that nobody is likely to have more than 50 slices, so I have only 4 by 3 for slices. But if somebody wants to try more slices, then he can even go to whatever number of slices he wants. Okay, so that was how these arrays are. This max slices helps us while getting these arrays dimensioned. So this is my x splitting, x and x1, x2, and this is my y splitting, y1, y2, and then I'm going to have 12 slices from 0 to 11. The index will go, and the total number of fissions, I want to record how many fissions are there in each corresponding to each slice. When I ran the first program, it already output this quantity. This was the number of fissions in the entire detector if you don't slice it. Now, when we slice it, we also change the effective acceptance. We don't we don't include the edges. So when we add up from all the slices, our final number is going to be somewhat smaller than this one. But then I want to record and print out the number of fissions in each slice, that was this one. And when I add them all up, then I will get this. So this also I would like to print out. So then, of course, here I just read the cut. The fission cut is read from here. From work.root, I recover the fission cut, and this is the chain and so on. The effective new part is this. In this loop, I have now introduced this one. You already know this is for selecting the fission. But this one, this is in the previous program also, x and y position calculation. But now comes this slicing. The slicing is done by a double loop. I have indexes ix and iy, which makes a double loop, and the way of combining the two indexes ix and iy into a single index is a pretty standard way of doing it in computer programming, and that is given over here. So I create a slice number by combining the x and y indices, and then I simply check. So this one does the checking of the x and y, that they are within the limits which are in my slice data.text, that is the x1 and x2, y1, where we should be inside those limits, and for each slice. And when we have done that, then I create that many histograms. So now hxy is not one histogram but 12. There are 12 histograms. They are filled with this command, and in this command I increment the number of fissions, so I will be able to see how many fissions there are in each slice. Then I have to display all these 12, so that is done over here. Just for my way of presenting, I have taken my screen coordinates, screen sizes, and then split it up so that all 12 are visible. You need not really spend time on this part of the code. It's just dividing the screen and then displaying. But for you, what is important is that this one. So you draw all the 12 spectra over here. I have again taken this double index method of looping and then combined the two indexes into one index. Then here I form the name like this, and then here I make sure that I have the z-axis in logarithmic scale, and then I finally draw it, and then I use this option called z, or you can use call, and then I plot this two-dimensional spectrum. So that's how I do, and then this is all for the display of the canvases. And yes, I need to print out the total number of fissions. I need to total number of fissions in each slice that is in this, and then when I add them all up, then how much I get in this I am printing out over here. So now we are going to compile lesson number 6. Lesson number 6 compilation command will be in the top of the program. This is your program 6 compilation command. I paste it here and then I compile it, and when I run it, just ignore the error and see the result. So I am running prog 6, and when I run prog 6, so these are my slices, these 12 slices it's showing you here, and see now these are the 12 2D histograms corresponding to the slices. So it's basically chopped off. You saw the big picture. This is the bottom left, and then the slice next to it, and then like that 12 slices. The last one here will be the top right. And so this is how I arrange my screen to show you the 12 slices. So up to now what we did, the aim was only to just to see how we can do the slicing and to make sure that we haven't made any mistake. That was the reason. We don't really need to display these slice pictures, but they are useful, and we should make sure that we haven't made any mistake here. We need to pass on to the real program, that is program number 7, and that program number 7 is going to actually calculate the neutron spectra corresponding to these 12 slices. I have 73 detectors, 12 slices. It comes to 876 neutron spectra, which I am going to calculate by one short program. The program will be very short, I assure you. It will be no longer than what you have already seen, and it will generate all the 876 spectra, and we are going to save it into an ASCII text file. So now come to program number 7. So this is program 7, and it's similar so far to whatever we did up to now. In the files, the slice data will be read as in the previous program. We will get 12 slices information from here. But now the spectra which we are going to build are going to be energy spectra, and I need to explain to you how the energy spectra are built, which is in my PowerPoint presentation, which I will once again show. And so this was the 12 slice thing, and this we have done. I need to make a small comment about the slices. More about this will come in subsequent lessons. But you see, you have decided on the slices and you have put this information in slice data.txt. So because this file is separate, so you can change this file and you can run it as you like. So if you decide to have only one large slice in the center, which some of the experimenters have been doing, this same program will do. You don't have to write another program when you change the decision about how many slices you have. You can repeat the analysis with a different number of slices. One program, it is structured, so you don't have to make changes. That's the benefit of structured program. Now, why do we do slicing? The slicing basically needs to be done because of the Watt expression which you are doing, the moving source fit. It's very much sensitive to angles. So if there is a spread in the angles, then it won't work. So you need to restrict the area of the detector we are working with. So if you slice it up, you will be able to use the entire detector data without discarding any data. On the other hand, the people who use only one slice in the center of the detector, they have discarded part of the data. So I would advise you not to do that. Try to analyze the entire data set without wasting any of your data. In fact, some of the experimenters, they do the analysis not only with just one slice, which they have restricted in size to take care of this angular size problem, but they have even restricted the number of detectors. So that is also very serious, because you have taken the data with a large number of detectors, but you are going to analyze only part of the data, that is few detectors. That also is wrong. You should certainly analyze all the detectors. Perhaps these experimenters think that it is very difficult to analyze the full data, but I am showing you here that if your code is well structured, and if you have, no matter how many slices you have, you can actually just with one code you can divide into as many slices as you want. You can include all the neutron detectors, and analysis time also, if the program is written optimally, the analysis time will not be much. We'll see that in the next lesson about how much time it takes for the analysis, but it's going to be quite easy. It's going to be small. It's going to be quite fast. The code is not only the code which I am presenting, not only it's well structured, but it's also optimized. So then the loops, the order of the loops is written in such a way that it runs fast. and then we will analyze all the data, so the overall statistics will not be reduced. We will I don't you see, so when you do the analysis moving source fit, you take in one go the entire data set. That means all the 876 spectra or whatever number you have decided according to the slices and the number of neutron detectors. That also will be a structured program, and it won't take long, and you will be able to analyze all your data. So I do not recommend writing first one small program or so-called small program which analyzes only one part, and then we'll worry about slicing later. So this is all not to be done. You should immediately have only one program and run that, which is structured and which is efficient. So why we have so many slices? This I explained. It is for getting the angles correct, and if the slices are larger, the errors introduced will be more. So we shouldn't have large slices. And then people ask, how can we make a simultaneous moving source fit if there are so many slices? The answer is that again it's a structured code which we will write, and it will be very easy. We'll see that in subsequent lessons, and you will be able to make the moving source fit with for all the slices simultaneously. And it is completely practical. Even if you want more than 12 also you can have, but we'll see later how many slices we really need. So right now I'm going to make my demo with 12 slices. And then some people ask, how can we present the data, because now we have got 876 spectra. Obviously we can't plot all of them on one sheet of paper and we can't have even in a thesis we can't have 876 spectra to be shown. So that is not a big issue. You can present some of the spectra as a sample, not all. And later on I will show you how we can have some combined spectra presentations where we can show several spectra which have been combined together. So this we will come to in subsequent lessons. The goodness of fit is decided by the chi-square only. So that chi-square number per point, that will come for all the data combined together, not from one spectra at a time. So don't worry about the statistics of one spectrum. Worry about the total statistics. Anyway, these are the questions that have to be taken up in subsequent lessons. I am going to show you this code, and this code is going to be small. The final root code has only 174 lines. It makes no compromises. You can have as many detectors as you want, as many slices as you want, and effective number of lines is around 100 or so, but the total program is 174 lines. This is how the program will calculate the neutron energy. The neutron, first of all, you need to work with the time calibration. So approximately, the TDC, if it has 4096 channels, and if the TDC range is set to 500 nanosecond, it works out to be 0.122 nanosecond per channel. You should actually, no, I don't have the TAC calibrator value. So if you have done the experiment, you should actually take a TAC calibrator or time calibrator, and you should calibrate the TDCs, and you should use the calibrated number, and you shouldn't use a fixed number like 0.122. I'm going to use 0.122 for all my channels, but in some of the experiments which I did, I found that even if you do the exact calibration, it's usually comes pretty close to this 0.122. So anyway, for my today's lesson, I have taken 0.122 for all the channels. If you can do better, and if you have got accurate individual calibrations available to you for all the channels, then please use it, and use it differently for each detector. So this is the way that you calculate the energy. Energy is going to be, of course, half mv square, and you should take the velocity of light as 29.979 in centimeters per nanosecond. And to calculate the time of flight of the neutron, you need to take the gamma. The gamma peak position is fixed, and that is available in my file which I have got, gpos.txt, which we had created in the previous lesson. And now we have p. The p is the channel number for the neutron, but that is variable. Event by event, this number will be different. and for each detector, but G is fixed for that particular detector, and that has been stored already in the file gpos.txt. Multiply the difference between the channel numbers by 0.122. This is the time calibration factor. And then you should add the time it takes for photons to reach, the time taken by photons to reach from the target to the detector will be 175 divided by the velocity of light. Many people leave out the second term. Actually, the second term is quite small, so you can decide, but it's works out to be around 4 or 5 nanoseconds. So I prefer to keep it. So let's go with that. So the time in nanosecond works out like I have shown here, 0.122 times the gamma ray position minus the channel number in for the neutron, and then the term 47.84. This is coming because of the time of flight of the photon. And then the energy is given by half mv square. For the neutron mass, you can take 939 MeV by c square. So 939.56 is the mass of the neutron in MeV, and divided by the time, divided by the velocity of light in centimeters per nanosecond, which is 29.979 squared. And then velocity. The velocity is 175 centimeters divided by the time in nanosecond. The time in nanosecond I have given in the previous equation. So this is your final, the one which is shown in the box. This is what I have coded. 1.076 into 10 power 6 divided by the gamma ray position minus the channel number of the neutron, and plus 47.84 coming from the finite time of flight of the photon, and this will be the result in MeV. So let's go ahead with this program 7. So program 7 is going to build for me 876 spectra based upon 73 detectors and 12 slices. The slice data is in that file, slice data.txt, so I read the slice data file, and this has in it the limits of x and y, and the number of slices it comes in that. So slice data.txt looks like this. 4 divisions I made along x direction, 3 divisions along y direction, and these are the limits in x and y direction. So it reads this file, and then my program 7 now knows the number of slices and the x and y limits, and then it makes it must, now the thing is we must read all the cuts for neutron selection. In addition to, you see, work.root had my fission selector cut, which was called as cut T1 T2. So that you can retrieve that as we did already. So this is retrieved. But then you also need to retrieve all the neutron selection cuts, the graphical cuts which select the neutrons in the plot of time of flight versus PSD. So that is there also in this same file work.root, and this get object will be able to retrieve all those. So that's the part where the cuts are now ready, and now comes the so this part, these are the initializers. So now how many constructors are there, because we are going to construct 876 spectra. The number of spectra is given by the number of detectors NDET multiplied by the number of slices. So 12 slices, and for me there are 12 slices, and for me there are 73 detectors, and that is 73. So that many spectra have to be initialized. So to initialize it, this is how you do. First you form its name. I have shown you how to do that with this form command, which is pretty handy here, and then now comes this line. So what I have done is I am going to go in MeVs from 0 is the minimum energy of the neutron. I am going to go up to 16. You will find that you don't really get high energy neutrons above 16. So I this is my choice here, 16 MeV. I limit my neutrons up to 16 MeV, and I decide to have 32 bins. So my step size in the neutron spectra is going to be half an MeV. Probably you can try with 0.25 MeV also. That you can decide, but here I have taken half MeV as the step size. Now the loop, and this is the main part of the program. The main part of the program is only this much which you need to concentrate. The rest you already know how to write, and there's not much there. So what do we do? And out of this also you know already this one. So you first make the fission selector. This is my T1 T2 gate. It is in these parameters, P0 and P1. I have made I ensure that I select fission only from the two MWPCs. Then so now if it's not fission, then I don't proceed further. So these loops, these are nested loops. So this is a loop over all the events. Then there is a condition put that if it is not, so this, all the loops and the conditions, they end up here in the same place. All these 5 brackets are together. So all these things are ending at the same place, so you need not worry. But if suppose it's not fission, then we do nothing because this goes up to the end. So we bypass this event completely. We select only the events which are fission events, and for those fission events we construct the X and Y positions by using the calibration values. Then we loop over the detectors. So I am having 73 detectors. You could have a different number, but we need to loop over it, and this loop also runs up to the end. Now inside that loop, we first check for each detector. We check whether you're inside the neutron selection, because you have neutrons and gammas, and we made the cuts and we have read back the cuts from work file. Work.root. So we now check that cut. So this is the cut n, this is your neutron cut, and for that detector that we are inside the cut, this condition is. We checked if we are not inside, there is not a neutron, you don't need to update any spectrum. So that's done. And now we calculate the neutron energy. The expression for calculating the neutron energy I have already explained on the slide, and it's given over here. It is the position, the channel number of the place where the gamma peak was there, that's called G or G pause, and then minus the neutron channel number, that's given by this particular parameter, and then I need to add 47.84, and then I need to square it. So that's done here. So I use this power function which is used for squaring. And so this is the formula, but I have taken one precaution. I have ensured that my neutron channel number comes to the left of my gamma peak, because this will always be true when you do it because of this gate. So if your this T cut is drawn correctly, then there won't be events where you have come close to the gamma or gone beyond it. So it shouldn't happen. But in case the cut is not drawn properly, you would get kind of unphysical spectra, or you would get error in this program running the power function. If you run, when this quantity becomes negative, then you get a situation which is an error condition. So to avoid that, I have just put it in the overflow. You see, my spectrum ends at 16 MeV. So I have pushed anything beyond this gamma to 20 MeV side. This is a precaution. Actually, it won't happen if the neutron cuts are drawn correctly. And that's it. And then slice. Now this is to be done. So the last innermost part is for slice. And for slice, I use two indices, Ix and Iy. And when I combine, the y goes in the y direction, x goes in, and then you have a combined index. So this is a standard way to combine indexes. Two indexes are combined into one. That's done over here. And then okay, so now I don't need to check these So this slicing checking is not done by using T-cuts. It's done by actually checking the limits, because T-cuts will be cumbersome as well as slow to use for slicing. It's much better done like this. So that's how I have done it. And then, okay, so in the core of the program, that is inside the innermost line where all the loops, all the conditions are satisfied, it executes just one fill command. So I'm trying to execute just one fill command, and everything else is are conditions and a loop, and it fills up my neutron spectra for me, and then I have finished. Now what's left is to, well, I decided to draw at least one of them to make sure that there's something coming. So I drew this one spectrum arbitrarily. Which one you draw? It starts at 0, so 0, 1, 2. So this is 2. This is my actually the third detector, and this is my 0, 1. So this is my second slice. That one I just drew one as a sample. You can actually draw all of them, but there are too many to draw, 876 of them. So you can draw some of them, you can decide. But I need to save them. Later on we are going to work with them. So I have decided to save them in an ASCII file rather than in a root file. The reason is we may use a program to analyze it which is not root based, we might use. So to make it easier to read, more friendly for that purpose, I did the saving here. Only two things. One is what are we saving? You must save the energy of the neutron. You must write it in one of the columns, and that I get as the center of the bin. You see, the bin has got a left edge and a right edge, and so I need, when I print it out, I need to print the bin center. That comes from this command, and the counts in that comes from get bin content. I am not going to normalize the spectra. You know that these neutron spectra are usually presented as double differential cross sections, and for that purpose we divide by the neutron efficiency as well as the relevant solid angles, and then the number of fissions. But that we will work out in subsequently in next lesson onwards. So for now I am saving the raw spectra as it is. So that's done over here. So that's all I wanted to say, except that now we should run it, and that will be our final run. So let's run it now. So let's go to my terminal. So in order to normalize with respect to fission, we need this number. So I had 12 slices, and each of these 12 slices, when I ran the previous program number 5, it showed me the number of fissions in those slices. When you add them all up, you get this number 202146, and this number 202146 is just slightly less than what we got the total number of fissions as 217989 in program 5, because this one was the entire detector, whereas now the boundaries of the detectors, the edges, we have avoided. And so that's it, and these are the individual numbers. This is useful for your normalization. These numbers need to be noted down, and they need to be applied when we do the conversion to double differential cross sections, and for the moving source bit purpose. Okay, let's now go over to our final program 7's compilation and running. So let's get it compiled first. To compile it, I need this first line of my program, and then I keep it here, and when I execute it, then here the compilation is completed, and now I am going to run. This command will run. Please ignore the error message. It's to do with my root installation. So here it's running. These are the slices, and it ran, and this is my final result. I plotted only one, so there are actually 876 spectra, but this is one of them. All the 876 spectra. So this is how it is. So I told you, I am going up to 16 MeV. So the energy spectrum starts at 0 and goes up to 16. So I have very few statistics. It's a very small sample file, so please don't worry. But later on you may get some counts going to slightly higher energies. I got nothing going beyond 7 MeV. These are the bins. The bins are half an MeV wide. So I got 32 channels from 0 to 16 MeV. Right. So yeah. So I need to tell you where that file is, and that's the file which you have created now. So when this program ran, it created this file which was not there before I ran. This is the file in which my results are there. So let me show you that file in detail. It actually goes slice by slice. So this is my first slice, slice number 1, and these are the coordinates or the limits in x and y for this slice, slice number 1. And then there will be spectra. There will be 73 spectra, because I got 73 detectors. So this is my first spectrum for detector number 1. It finishes here. Then it goes to the second spectrum, but for this first slice only, and like that it goes on. So if you go to here, then this is slice number 2 start. So slice number 1, at the end of each slice I have put this this kind of separator line, so that it becomes a bit easier to read. And then see now slice number 1 was completed, and this is now slice number 2. Okay, so again slice number 2, detector number 1, then it will be followed by detector number 2. So this is the spectra. In each spectrum, this is your center point of the bin, and these are the counts in it. So 0.25 was the center of the bin, then 0.75 was the center of the second bin, and like that it went on, and 15.75 was the center of the last bin, and then you have the counts in the next column. So like this it goes on, and you have the last detector, that is 73rd detector, but for the last slice. Before that you will have the previous slice, so this previous detector. This is the last sorry, so this is for the last slice and all the detectors. So 73rd detector, last slice, this is for the also last slice, but 72nd detector, and like that. So that's how the final result has come. So all your work in such a short program, you have been able to generate your 876 spectra, or more or less depending upon your requirement and your experiment, can be generated with a very, very short program. Doesn't have many lines. Its execution is also fast. In the next lesson, I will try to focus on how fast this code is, how you can run it for your actual data, and some of the things which you may need to do when you try to work with real data rather than just a small sample file. But for now, this is today's lesson. So bye for now, and see you in the next lesson.